So, hello all. I'm Gitanjali. I'm a PhD scholar from IIT Delhi. So, I welcome you to the to this live section of the course Quantum Mechanics 1. So, in this section, we will solve some of the problems that will help you to understand the concept better. So, in the last class, we have solved some of the problems related to the angular momentum. So in this section, we will solve the problems that is related to the concept that has been uh, studied in this week. So in this week, you have studied about the CG coefficient. So whenever you have a composite system, like you have more than two particles, what will happen? So in that case, we will have a total angular momentum. So in that in that system, in composite system, you can represent it in terms of either a coupled state, coupled eigenstate, or in terms of a uncoupled eigenstate. So, and these coupled and uncoupled eigenstates, they are related by CG coefficient. So, some of the these CG coefficients, you can easily derive it using the orthogonality condition as well as using the raising and lowering operator. So let me share my screen first so that we can start solving the problems. So this CG coefficient, you have already studied. These CG coefficients are non-zero whenever. So let's say you have two particles. One have angular momentum J1 and other one is angular momentum J2. And the magnetic quantum number are M1 and M2. So in that case, the CG coefficient will be non-zero whenever the total magnetic quantum number, that is M, that is not equal to M1, that is equal to M1 plus M2. So whenever M equal to M1 plus M2, then its CG coefficient is non-zero. And in addition to this condition, there is another uh, condition that is required for a non-zero value of CG coefficient. That is when J value, the total angular momentum J, whenever the J value lies between the maximum and minimum value, like the maximum value will be J1 plus J2 and the minimum value would be J1 minus J2, right? So in that case, you will have a non-zero value of CG coefficient. And so in general, if there are two particles, then you can the J1 and J2 values, they are not they are generally different. So if that is the case, then the degeneration of the system, you can get it if the degeneration will be 2J plus 1. So if J1 is less than J2, then the degeneration will be 2J2 plus 1, only 2J1 plus 1. And if J2 is less, then it will be J2, 2J2 plus 1. So whichever value is less, whichever J value is less, that will determine the degeneration of the system. My tab is not working, so let me share my screen. I think you all can see my screen. So, can anyone please confirm whether my screen is visible or not? Okay. Sorry for today. Actually, my tab is not working, so I have to show the solution using my laptop. Okay. So before start solving the CG coefficient, let us see the problems that I have left in the last class. So there are two problems that I have not solved in the last class. So first we will solve these two problems. Then after that we can start solving the CG coefficient and the problems that is related to that concept. So the first problem, let us see the first problem. So the first problem is easy. So it let me maximize it. So it tells about derive the matrices. Derive the matrices for the operator j square, jz, jx, and jy for j equal to 3 by 2. Let me highlight it. So the question is asking about the matrix representation of these operators when j equal to 3 by 2. Okay, so when j is first, what you have to do, you have to see the dimensionality of the system. So when j equal to 3 by 2, the dimensionality will be 2j plus 1. So 2j plus 1 means 2 into 3 by 2 plus 1. So it will be 4. So you will get a 4 cross 4 matrix. So, and for j equal to 3 by 2, the allowed values of m will be 3 by 2, half, minus half, and minus 3 by 2. So this is you already know, like when j equal to 3 j equal to some value, then the values of m, it ranges from minus j to plus j in steps of 1. Now, to determine the matrix element of j square, what you have to do, you have to take the expectation value of j square in two different state. One is jm and other one is j prime and m prime. And j square, you already know that j square, when it acts on jm, it will give j into j plus 1 h cot square, right? And the remaining will be the Kronecker delta function, that is delta j j prime and delta m m prime. So j and j prime are same because j is 3 by 2. So it means the term that will remain, that will determine the non-zero coefficient, will be the Kronecker delta m and m prime. Okay. So now 1 minute. So whenever for j equal to 3 by 2, what will be the value of j into j plus 1? So it will be 3 by 2 to 3 by 2 plus 1 h cot square. So the j into j plus 1 you will get is 15 by 4. So the component, the matrix component of j square will be 15 by h cot square by 4 delta mm prime. So this delta mm prime will decide what will be the matrix component for j square. So the matrix that you can write, you already know it is a 4 cross 4 matrix, and there is a constant term here which is 15 h cot square by 4. So the remaining will be delta m and m prime. So you know that m, the maximum value of m is 3 by 2, right? It is 3 by 2. So what you can do? So you start from 3. You take 3 by 2, m equal to 3 for the first row. What you can do? You take m equal to 3 by 2 and keep it as a constant. Now you vary the value of m prime. So when j equal to 3 by 2, m and m prime will take same values, like when they will take value from 3 by 2 to minus 3 by 2 in steps of 1. So the m prime, that's why I varied m prime from 3 by 2 to minus 3 by 2 here. Like I have kept m as a constant and I have varied m prime. This is half, this is minus half, and this is minus 3 by 2. Similarly, for the second row, what you can do, you change the value of m. Like I have changed the value of m is m from 3 by 2 to half. So I have changed the value of m. Now what you can do, use similarly in the same as the first row, you use just change the value of m prime from 3 by 2 to minus 3 by 2. You change it from 3 by 2 to minus 3 by 2. And for the third row, you change the value of m to half to minus half. And similarly, change the value of m prime from 3 by 2 to minus 3 by 2. And for the fourth row, the value of m is minus 3 by 2. And the m prime value, it changes from 3 by 2 to minus 3 by 2. So now, by looking at the value of m and m prime, you can easily determine whether the component, the matrix component is 0 or not, right? Because it is a Kronecker delta function. So whenever they are equal, then you will get a non-zero value. And whenever they are not equal, you will get a zero value. Whenever they are not equal. So if you see, then you can easily observe that these diagonal elements, they are in the diagonal elements, all value of m and m prime are, sorry, this one and the fourth one. So for all this value, the m and m prime are same. That means only the diagonal elements are non-zero and other off diagonal elements are zero. So in this way, you can easily determine what is the matrix representing the J square operator. Okay. So similarly for J square, you have already determined. Now for JZ, you know that for JZ, the eigenvalue is mh cut. So instead of J into J plus 1 h cut square, you will see mh cut delta m and m prime. So similar to the J square J square matrix, where I have changed like this matrix. Oh, for JZ also, you have to write the Kronecker delta expression for each component and see whether the m and m prime are same or not. If they are same, then it is 1. If they are not, then it is 0. So if you see, then here also only the non diagonal elements are non-zero and the other off diagonal elements are 0. So if you see the first diagonal element, it will be delta. If you see J square term, then this will be delta 3 by 2 and 3 by 2, right? So let me change the color. So for JZ, it will be 1 minute. So the first term will be delta 3 by 2 and 3 by 2. So that means the value of m will be 3 by 2, right? 3 by 2 h cut. And if you see the second term, it is delta half and half. So that means you will get m value half. So it will be half h cut. And similarly, the third one will be minus half h cut. And the fourth one will be minus 3 by 2 h cut. So now you just take out the common factor, which is h cut by 2, and represent the JZ matrix. So in this way, you can uh, calculate the matrix representing the JZ operator. Now for other two matrices, that is JX and JY, what you can do, you use the ladder operator. Like you can express JX and JY in terms of ladder operator. JX is nothing but, if I show you, JX is J plus J minus by 2 and JY is 1 by 2y, J plus minus J minus. So, and the matrix element for J plus and J minus, you already know. For J plus, it is like this. It is H cut root over of J into J plus 1 minus M into M plus 1. And there is a Kronecker delta term here. And J and J prime are same. So that means this will be all depends on the value of M prime and M plus 1. So instead of M and M prime, here we have for J plus operator, you have M prime and M plus 1. So for the matrix, what you can do, similar to the previous matrix where for the first row, I have kept the value of M as a constant, which is 3 by 2, and varied the value of M prime from 3 by 2 to minus 3 by 2. So in this case also, what you can do, you just keep for the first row kept the m constant, which is 3 by 2, and vary the value of m prime, and check whether the components the m prime and m plus 1 are same or not. If they are same, then they will give a non-zero value. So if you calculate in this way, then what you can see, only the for j plus operator, only the 1 2 element, then 2 3 and 3 4, these two three elements will be non-zero and other elements will be 0. Okay, so this is for J plus. Now for J minus, you follow the same procedure. Like for J minus, the matrix component will be h cut root over of J into J plus 1 minus M into M minus 1. And delta, instead of M plus 1, here we have M prime and M minus 1. Okay. So now you change for the matrix represented representation. What you can do, you just keep the value of m as a constant and vary the value of uh, m prime from minus 3 by 2 3 by 2, and check which components are for which components these matrix elements are same. Matrix elements are non-zero. So if you see, then you will see there is a the 2 1 element, then 3 2 and 3 4 3. These elements will be non-zero, and the if you keep root 3 root 2 and root 3 2 and root 3, you will get it from by putting the value of j and m here. Okay, so now from 1 and 2 you have j plus and j minus, so you can easily calculate what is the matrix for jx and jy. Okay, so for Jx, it will be half of J plus and J minus. And for J minus, sorry, this will be Jy, not J minus. It will be Jy. So for Jy, it will be 1 by 2y, J plus and J minus. Now you have already have the J plus and J minus matrix. So you can easily calculate what is the matrix for Jx and Jy. Okay. So this is one of the problem that is related to the orbital angular momentum. So do you have any query in this problem? Otherwise, I will move to the next question. Okay, let us move to the next problem. So after this problem, we will start solving the CG coefficient, the problems that is related to the CG coefficient. Um, so let us see the problem. So it's based on the Hamiltonian and a charged particle in a magnetic field. So let me read out the question for you. So it is asking, write down the Hamiltonian for a spinless charged particle in a magnetic field, and so that the Gauss transformation, that is when the potential AR goes to AR plus the gradient of F is equivalent to multiplying the wave function by a factor, by a phase factor exponential, i.e. FR by H cot C. So it is telling, asking about write down the Hamiltonian when a spinless particle is in a magnetic field, and it is asking about whether when you do the Gauss transformation, then in that case the wave function wave function only changes by a phase factor, which is this. So you can relate the initial and final wave function by means of a phase factor. Okay. So the Hamiltonian. Hello. So the Hamiltonian for a spinless particle. So you can write it as a by equation 1, which is h equal to 1 by 2m p minus a by c a cap whole square. Okay. So this is the Hamiltonian for a spinless particle in the presence of external magnetic field. This formula you have to remember it. And the A here, the A is a it is related to the magnetic field B. So you know that the B can be you can get the magnetic field B from A, that is B equal to call of A. Okay. Now this Hamiltonian, it satisfies the Schrodinger equation, right? So if you put the Hamiltonian equation 1, then you can easily write what is the expression for Schrodinger equation in the presence of a magnetic field. So this is, if you see equation 2, then this expression is the Hamiltonian expression, and this is the wave function, and is the energy eigenvalue, and psi is the initial wave function. Now, if you now, how can you check whether in the presence of a Gauss transformation, the wave function only changes by a phase factor? What we can do here is we first take that. Let's take the wave factor uh, changes by a phase factor under the condition of Gauss transformation. Now, what we will prove is we will prove that under this phase variation, we will get the same eigenvalue E. Okay, if it satisfy the, if after Gauss transformation, if it satisfy if we get the same eigenvalue E, then it proves that under the Gauss transformation the wave function changes by a factor, changes by a phase factor, which is exponential IE FR by H cot C. Okay, so that's why I have taken, suppose A changes according to the Gauss transformation. That is, when under Gauss transformation, the A will become AR plus delta F R. Now we have also taken that, let's take the wave function under this Gauss transformation, it changes by a phase factor. Like psi goes to psi prime r, and this psi prime r is related to the initial wave function by a phase factor exponential I fr by h cot c. Now what we will prove? We will prove that under this transformation, the energy eigenvalue E, that will remain same. Okay, if that remains same, then we can conversely prove that this wave function are related by phase factor. So this if you now uh, so this is equivalent to proving, this is what I was telling, that if under Gauss transformation, if psi goes to psi prime r, then the energy eigenvalue E will be remain same. So now let us prove the equation 5. Okay. So now let us see the left hand side. So left hand side is P minus E minus C A prime square. Let us take the first one without the square. So P minus E by C A prime psi prime R. So now you can use the linearity of combination linearity property of this operator P and P prime P and E by C A prime. So you can easily write this one is this combination. Now what you can do, you put the value of A prime here. Okay. So you have put the value of A prime as AR plus delta FR. Now what you can do, you use the operator expression for P. So P, you know that this is minus IH cot delta, right? So you just, for the first term, you have put the uh, operator expression for the momentum. Now what you can do, you just operate this delta operator, this gradient operator on this wave function psi prime r. Okay. So if you operate it, then it will first act on this by keeping the exponential factor as a constant. Then it will act on this by keeping psi of r as a constant. Okay. So this is what I have written here. So first it will act on psi of r by keeping this exponential constant. And second, it will act on this exponential factor. If a delta acts on exponential factor, then you will get a constant term here, which is IE delta FR by H cot C is psi of R. So now in the third, this line, I have just included this minus IH cot C. I have take it inside. So you will get minus IH cot delta psi R and E by C delta FR psi of R with the exponential factor IE FR by H cot C. So now if you check this term, this is minus IH cot delta psi of R. If you compare it, so if you compare it, it will be nothing but P psi of R, right? So minus IH cot delta, I have put it P of psi of R, and there is this terms. Now what will happen? This equation 6, now you have act this one time on psi of R. So now you have to again act this operator on psi of R because there is a square. So if you act this one on this state, then what you can get will get is you will get terms like this. Okay. So you have to just use the operator expression and use the linearity properties of this operator. So if you put it, then the final expression you will get is this one. So this means this is, and this expression is nothing but, if you check this expression, this is psi of r multiplied by a exponential factor. So this is nothing but psi prime r. Okay. So that means you P, if you act, so this term, this left hand side term, we are checking this term. So this term you get P E minus C A psi prime R. Okay. So that means the left hand side of this equation is this. So, and this one is nothing but E, right? This one is E psi of R, right? If you check, let me show you this one, the second equation. If you check second equation, then when this 1 by 2m P E minus C A prime acts on psi of R, it will give E psi of R. So that means here we will get E psi prime R. Okay. So this proves that the wave function is under the Gauss transformation, we will get the same eigenvalue E. So this means that if you take a Gauss transformation the wave function only changes by a factor e, which is exponential. Let me show you here. This is exponential IEFR by h cot c. Okay. So this is how you can prove this question. So I think this problem is clear to you. If not, then you can ask me. Otherwise, let me move to the next question. Do you have any query in this question? Because it was a long question. So if you have any query, then you can ask me. So these are the two problems that I have not solved in the previous section. So let us move to the CG coefficient problems. Please go through the question third once before solving this question. Please go through this question. Third question. Meanwhile, I can check whether my tab is working or not. Let me read out the question for you. So it is telling, consider two particles which have total angular momentum J1 equal to 5 by 2 and J2 equal to 1. So you have two particles which have J1 equal to 5 by 2 and J2 equal to 1. Now the maximum and the minimum allowed values for the total angular momentum of the composite system are respective. So you have two particles. One is angular momentum J1 equal to 5 by 2. Other one is J2 equal to 1. Now it is asking about what is the maximum allowed value for J in this composite system and what is the minimum value of J in this composite system. So you know that this J it acts vectorially, right? When J equal to, you know that this is J1 plus J1 plus J2. It acts vector. You do a vector addition for J1 and J2. So that means the maximum value of J will be J1 plus J2 and the minimum value of J will be J1 mod of J1 minus J2. So J1 and J2 are already given to you. One is 5 by 2, other one is 1. So it means the J maximum value will be 5 by 2 plus 1, which is 7 by 2. And the minimum value of J will be 5 by 2 minus 1, which is, I think, 3 by 2. So that means the answer will be fourth option, which is J maximum equal to 7 by 2 and J minimum equal to 3 by 2. So it is based on the concept. If you know the concept, then you can easily solve this problem. It is a two-line solution only. So this is how you can solve this one. So now let us move to the next problem. So the next problem is, so let me read out the question for you. The matrix element LM1, Ly, and LM2 will be. This matrix element will be non-zero if the first option is mod of M1 minus M2 is greater than equal to 3. 1 minute. and B, it is non-zero if M1 equal to M2 plus or minus 1, or it is 0 if M1 equal to M2 equal to M1 plus or minus 2, or it is 0 if M1 equal to M2. So it is asking under which condition this matrix element is 0 or non-zero. So for that, what you can do, you have to simplify this matrix element. So Ly, you already know the expression for Ly in terms of raising and lowering operator. So for what you have to do, you have to express Ly in terms of raising and lowering operator and find out the individual, simplify the expression individually. Okay. So let us see the steps. So Ly, you already know Ly is nothing but L plus minus L minus by 2y. Okay. So that means if you take this matrix component, so it will be nothing but the bra of LM1, and there is a operator here which is Ly, and the kate of LM2. So now what you can do, you operate this L plus on this kate, L plus and L minus. So you operate it and find out what will be the simplified expression. So if you operate it, then you can write it as this bra LM1 with L plus acting on LM2, and the second component will be LM1 L minus operator acting on LM2. So if you don't know the what will be the coefficient, like when L plus acts on M1 or M2, then it raises the value of M by 1. So if you don't know the coefficient that is attached to this kate, then let us fix this coefficient as C1. Let us take the coefficient, the normalized coefficient is C1. So when L plus, when it acts on LM2, it will give C1, and the kate will change to L M2 plus 1. Okay. Similarly, when L minus, when it acts on LM2, so it will also, sorry, it will lowers the state of the system. Like if it takes M2 to M2 minus 1. So that is why there is a kate here, which is L M2 minus 1. And there is a constant of C2, which is related to root over of L into L plus 1 minus M into M minus 1. So this constant factor, I have not written it explicitly. Now, if you check this one and this, so these are nothing but the Kronecker delta expression, right? Let me change the color. So these are nothing but the Kronecker delta expression. So for the first term, you will get delta M1 with M2 plus 1. And the for second term, this will be M1 and M2 minus 1. So if you check this, then this Kronecker delta will be 0. It will be non-zero whenever this M1, these two terms indices are same. Whenever these two are same, then this will be non-zero, right? So that means it will be non-zero. The first condition is, if you see the first condition, this one. So here I have written, it will be, the matrix coefficient will be non-zero whenever M1 equal to M2 plus or minus 1, or it will be 0 otherwise. Like when M1 equal to M2, then this Kronecker delta will be 0. For these two coefficient, you will get a 0 values of Kronecker delta. Okay. So that means whenever M1 equal to M2, you will get a 0 value of matrix coefficient. And whenever M1 is M2 plus or minus 2, in that case also it is 0. So these two condition I have taken because it's already given in the question. So it is given in the if you check B, non-zero if M1 equal to M2 plus or minus 1. That we have checked. It is non-zero whenever M1 equal to M2 plus or minus 1. And the next is whether it is 0 if M2 equal to M1 plus or minus 2. So this condition is also satisfied. And the third is whether it is 0 if M1 equal to M2. So this is also satisfied. So in the problem, you have to check each option, whether they are satisfying the condition or not. After that, you can write the answer. Okay, so for this problem, you have three answers. So in this way, you can find out the matrix element, whether it is 0 or not. Now let us move to the fifth question. Do you have any query in this problem? Okay, otherwise, let us move to the next problem. Okay. So the next problem is, it is asking whether this expression, that is the inner product of Jm with state J1, J2, M1, M2 is 0 when M1 is when M equal to M1 plus M2. So it is asking about whether this condition is true or not. So you know that this Cg coefficient, this is nothing but the Cg coefficient, right? This one. This is the product between a coupled state with a uncoupled state. The first one, if you see the first one, this one. So this is the coupled state and this one is the uncoupled state. So with this it's asking whether the Cg coefficient is 0 when m equal to m1 plus m2. So you already know that the Cg coefficient is non-zero whenever m equal to m1 plus m2. So that means this statement is not true, it is false. Okay, so this is how you can check whether the Cg coefficient are 0 or not. So for non-zero value, we have to check whether the m values is equal to m1 plus m2 or not. If it is equal to m1 plus m2, then in that case, you can state it is non-zero. And if not, if m equal to not, if not m not equal to m1 plus m2, then in that case it will be 0. So the answer will be B, which is false. So this is also one of the conceptual question. So it's a one-line solution. If you know the concept, then you can easily approach this question. Now let us move to the next problem. Six. So please go through the question once. So let me read out the question. So the question is like this. There are two particles, one in the state J1 M1 equal to 4 and 2. So for first particle, J1 is 4 and M1 is 2. And the other in the state J2 M2, which is 1 and -1. Okay, so for this state, the J2 will be 1 and M2 is -1. Now, if for this two particle system, you can write the couple state is J1, J2, and Jn, right? This you already know. Now it is asking how many different states are there in the old representation 4, 1 and M1, M2. So it is asking about the states that is present in the old representation, that is uncoupled state. So uncoupled state, you can write it as J1, J2, M1, M2, semicolon M1, M2. So for for this one, J is equal to 4 and M equal to 1. So the number of state in the old representation, how you can calculate it? So this will be equal to the multiplication of 2J1 plus 1 and 2J2 plus 1, right? So it will be 2J1 plus 1 and 2J2 plus 1. J1 and J2 are already given. J1 is 4. So if you see, J1 is 4 here and J2 is 1 here. So that means if you put the value of J1 and J2, then it will be 2 into 4 plus 1. The other one is 2 into 1 plus 1. So it will be 9 into 3. So the total number of state will be 27. Okay. So this number of states will be there in the old representation, that is uncoupled state. Now let us move to the next one, next part of this question. 6b. So, so the question on 6b is like, what are the possible values of J and how many states are there corresponding to each possible values of J? So the possible values of J you can easily find out. J will be, if you have two particles J1 and J2, then the J will be range from J1 plus J2 to J1 minus J2, right? So the possible values of J will be J1 plus J2 to mod of J1 minus J2. So J1, J2, J1 plus J2, you know, J1 is 4 and J2 is 1. So it will be 5 and this will be 3. So in between 5 and 3, you will have one state which is 4. So you will have total 3 values of J, which is 5, 4 and 3. Now for each value of J, like 5, 4 and 3, the M will have different values. M will have values from minus J to plus J in steps of 1. So total values will be 2J plus 1 for each value of J, right? So if let's say we have J equal to 5, then M, the total values of M will be 2J plus 1. And J is 5 here. So that means the total values of J will be 2 into 5 plus 1. And that will be 11. So you will get 11 here. Now for the fourth one, for J equal to 4, it will be 2 into 4 plus 1. So we will have 9 here. And for 3, it will be 2 into 3 plus 1. So total will be 7. So that means the total possible values of J will be For j equal to 5, it is 11. For j equal to 4, it is 9. For j equal to 3, it is 7. Now let us, this is also conceptual. So I am solving this concept because it will help you to understand. It will help you to understand the concept, as well as it will help in small problems, because many of the students, they stuck in this even in the simplest problem. So if you know the concept, then you can easily, within 1 minute, you can find out the answer. Now let us see the third part of this question. So do you have any query? You have any doubt till now? Okay, so let me move to the next problem then. So the next problem is this one. So let me read out the question for you. So the problem is, it is in the continuation of these next two problems that I've solved before. So it is like this: which of these state in the old representation, which is this one, 4, 1, M1 and M2, are the eigenstates of J square and Jz, where J is the total angular momentum operator. So it is asking, the in the old representation, you have different kind of state, right? You have 2j plus 1 states. You have seen it is 27 state, right? So in that 27 state, how many states are the eigenstates of j square and jz? So if you see the old representation is a uncoupled basis gate, right? It is the uncoupled basis gate. Now, if this uncoupled basis gate is a eigengate or eigenstate of j square and jz, that means this uncoupled and coupled state. So j square and jz, we represent it in the coupled state, right? So for the coupled state, the matrix represent the basis gate is like j1, j2, and jm. For uncoupled, it is j1, j2, m1, m2. So that means for the uncoupled state, which is 4, 1, M1, M2, it is asking whether it is a in this basis uncoupled basis gate, how many gates are the eigengates of this coupled basis gate. Okay, so in the, if you recall in the lecture, so there is a concept of staged gate. So staged gates are those for which the m1 value takes the maximum value of j, and m2 also takes the maximum value of j. Maximum m1 takes the maximum value of j1, and m2 takes the maximum value of j2. That's why the in the coupled state, the m takes the maximum value of j1 and j2. So these are the stretch gate. So you have already seen, for the stretch gate, these stretch gates are directly related to the uh, uncoupled basis gate. For other state, like other than this stretch gate, the other gates are like the linear combination of this uncoupled basis gate. But if you have stretch gate, then it is directly related to the coupled basis gate. So that means only the question here, in the question, for the answer is the stretch gate. So the stretch gates are the stretch gate that is present in the uncoupled basis gate are the eigenstates of j square and jz. Okay, so if you have to find out the stretch gate, So this is I have written the same. Like I have told you ki in other cases the coupled states are represented by linear combination of uncoupled basis state. Like if you recall in the lecture, the up and down spin state in the coupled state is related to the up and down. It is related to the linear combination of down up and up down. So that means so the stretch gate for J1 equal to 4 and J2 equal to 1. So already J1 and J2 are given. It is given here. It is 4, 1. So for J1 equal to, if you see the first option, J1 equal to 4 and J2 equal to 1. So M1 can takes the maximum value of J1, which is 4, and M2 takes the maximum value of J2, which is 1. So that means the one of the stage gate is 4, 1, semicolon 4, 1. And the other one is the extreme minima point. Okay. So for J1 equal to 4, M1 can take the minimum value -4. For J2 equal to 1, M2 can take value -1. So that means the stage gate is 4, 1, -4, -1. Okay. So these two stage gate, they are directly related to the uncoupled basis gate. So that means these uncoupled stage gates are the eigengates of J square and Jz. So this will be the answer to the question. Now let us move to the next problem. Please go through the question once. 60. So it is based on the CG coefficient. It is asking you to find out the CG coefficient. So let me read out the question for you. So the question is find the CG coefficient for 4, 1, 4, 3 uncoupled state with 4, 1, 2, 1. Okay. So you have to find out what is the CG coefficient of a coupled state with a uncoupled state. So how you can approach this type of problem? For this, what you have to do, you have to start from the stretch gate. So you have to start from the stretch gate, then you act the raising and lowering operator. So if you act the raising and lowering operator, then you can and also use the orthogonality condition. So if you use these two conditions, then you can easily find out what will be the CG coefficient for this inner product. Okay, so that's why I've started with a stretch gate, which is 4, 1. So the maximum will be, so J1 is 4 and J2 is 1. So let me show you J1 and J2. It was already given in the question. So J1 here is 4 and J2 is 1. So that means the maximum value of J that will take is the maximum value of M will be 5 and the maximum value of J will be 5, right? So this is the coupled state expression, which is J1, J2, Jm. This is the stretch gate. Now this stretch gate, for 5, for m to be 5, the value of m1 have to be 4 and the value of m2 have to be 1. So that means this coupled stretch gate is related to this uncoupled basis gate 4141. Okay. Now to find out what value of this inner product, what we can do, we will act the lowering operator J minus. So in the second line, I have act J minus here. So when J minus will act on this 4155, so it will lower the value of M. So it will lower the value of M to 4. Okay. So the value of M will get lowered from 5 to 4. And there will be a constant root over of 10. So this root 10 you can easily check. It is root over of so when J minus acts on J, you got like root over of J into J plus 1 minus M into M minus 1, right? So just Jm values are already given. Jm is 5 and here also M is 5. So just put the value of J equal to 5, M equal to 5 in that root over of expression. So if you put it, then you will get root over of 10. Okay, now this state will be get changed to, instead of 5 5, you will get 5 4. Now if you see the right hand side, so J minus, here you can write it as J1 minus the lowering operator for J1 with tensor product with 1 plus J, identity cross J2 minus. So J minus, what I have done, I have split it into two components. What is one is J1, other one is J2 lowering operator. Now this two operator will act on this uncoupled basis gate. Okay, so they will act on this uncoupled basis gate. So J1 will act on the first basis gate, and it acts as an identity in the next state. Next uncoupled state, and J2, for J2 it doesn't act, it acts as an identity in the first uncoupled state and acts in the second eigengate. Okay, so if you do it, so what we will get is root over of 8. So J, if you see the value of M is, so let me, so 1 minute. J1, J2 and M1, M2. Okay. So this J minus, so this is nothing but, if you, so let me, so this J minus will act on this M1. Okay. It will act on 4, right? It will act on M1. So the M1 will get reduced to 3 here. Let me change the color. So J1 minus would act on this 4. Now this J2 minus will act on 1. It acts on M2, right? So 1 will get reduced to 0 here. That is why there is a 0 here and there is a 3 here. Now root over of 8 and root over of 2. You get it from the coefficient, that is root over of J into J plus 1 minus M into M minus 1. So if you put the value of J1, J2 for first case, for this coefficient, it will be root over of J1, J1 plus 1 minus M1 into M1 minus 1. But for the second one, it will be root over of J2, J2 plus 1 minus M2 into M2 minus 1. Okay, so if you put the value, J1, J2 value is already given. J1 is 4, J2 is 1, and M1 is 4, M2 is 1. So if you put it, then you can easily get root over of 8 here and root over of 2 here. Now, this in the final, in equation 1, I have rearranged the terms. So I have taken root 10 from left hand side to right hand side. So now you got the gate, the next lowering state nearer to the stretch gate, which is 4154. You can write it as a linear combination of these two uncoupled state. The first one is 4131 and the second one is 4140 with a coefficient. Now in the question, they have asked about 4143, right? So to get 4143, the value of m is 3 here. So what you can do, you again act a lowering operator on this state. So if you act it, then it will get reduced, right? So before doing that, we already know that this 4144. So before coming to 3, we have to check the expression for 4144, right? So after that, we can act a lowering operator and get the value of 4143. So 4144 is, you already know it is orthogonal to 4144. So if you take the inner product, then it will be 0. So that means, yeah, to get the expression for 4144, what you can do, you just interchange this coefficient. So 4144, you can easily write it as a linear combination of 4131 and 4140. And to find out the coefficient, what you have to do, you have to interchange the coefficient, like take this one and put it here for 4142 and take this one and put it here. Okay, so this is what I have done. I have taken root over of 4 by 5 and multiplied with 4140, and I have taken root over of 1 by 5 and multiplied with 4131. So to make it 0, we have to take a minus factor so that the summation will be 0. Okay, so this is how you can find out the expression for 4144. Now you already got the expression for 4144. Now what you can do to get the value of 4143, the question is asking about 4143. So you can act a lowering operator here. Okay, so if you act a lowering operator, the value of m will get changed to 4 to 3. So it will get changed to 4 to 3. So let me, so this is how you can approach. So I have act J minus on 4144. So J minus, you can write it as J1 minus cross product identity plus identity cross J2. This is how you can represent J minus in a two particle system. And there is a, this state is, this you already got from, I think, equation 2. This is equation 2 for 4144 expression. Now what you can do, so you know that this J1 minus, it will only act on the first state, okay, the first uncoupled state. So it will act on 3 and it will reduce it, the value of 3 to value of m to m minus 1. So and the J2, it will act on 1. Okay, it will act on 1 and get it will reduce the value of m from 1 to 0. So in the next line, if you see, this is if I go from here to here, this is nothing but when J minus acts on 4144. So when it acts on J1 acts on 4144, you will get 4143. The value of M will reduce to 3 here. Now for the coefficient, it is root over of J into J plus 1 minus M into M minus 1. Now what you have to do, you have to put the value of J and M. So J and M value are nothing but, if you see, these are the value of J and M. So J is 4 and M is also 4. So if you put it, you will get a root over of 8 here. This is the left hand side of this equation. Now if you see the right hand side, so in the right hand side, what I have done, so I have uh, take the other notation for this uncoupled state. So this 4131, this state you can write it as 43 cross 11, right? This is the other notation for the uncoupled state. Similarly, for 4140, you can write it as 44410, right? You can write it like this way. Okay, so I have just changed the expression. So these are same, only I have changed the uncoupled notation. So now what will happen? So this J1 minus, so let me change the color first. So this J1 minus, so here J1 minus will act on this also and it will act on this also, right? So this two action I have written in this first word. This is the first word. And for second line, it is J2 minus acting on this one and J2 minus acting on this one. So this is the second line. So this is when J2 minus acts on the two states. So now if you check the first line, so J1, it will act on this one, it will act on 3. Similarly, J1 here, it will act on the first gate only. While for J2, it will act on the second gate, and here also it will act on second gate. So now what you have to do, you have to just find out the expression for this. So you have to just find out the final expression. So you have to find out what will be the value of J1 when it acts on 4, 3, and what is the expression for J1 minus when it acts on 4, 4, and J2 minus when it acts on 1, 1, and the other one is J2 minus when it acts on 1, 0. So this one is similar to so what you have to do, you have to use the expression like for J1, when J1 minus acts on J1 M1, it gives J1 into J1 plus 1 minus M1 into M1 minus 1, right? Into each code. And the value of M will get lowered by A1. So if you see the first, this term, so this term, the first one, initially there was 4, 3, right? Here this was 4, 3. Now when J1 minus acts on it, it will get changed to 4, 2. The next 1, 1 will remain unchanged. And these are the coefficient that we have to calculate it by taking root over of J1 into J1 plus 1 minus M1 into M1 minus 1. And if you see this one, J1 minus 1 acting on 4, 4, you will get a ket 4, 3 here, and the other ket will remain unchanged. And this is the constant factor that you will get if you put the value of J1 J1 and M1. Now for this one, this is when J2 prime acts on 1, 1. So when J2 prime acts on 1, 1, you will get 1, 0. And there is a constant term here, which is minus 1 root 2 by root 5. And the last one is J2 minus acting on 1, 0. J2 minus acting on 1, 0. So you will get 1 minus 1 here. So this constant, I think you can easily calculate by putting the value of J2 M2. So now you just have to rearrange the total expression and you have to write the whole expression. So if you rewrite it, you will get an expression like this. Now the 4143, we can easily calculate it is root over of 7 by 20, 4121 with plus 3 by root 2, 4130 and 1 by root over 5, 414 minus 1. So let us see the problem. So the problem was asking about what will be the component. What will be the inner product of 4143 with, so let me erase so that you can easily see. So the question was about 4143 acting on 4121. So you already got the expression for 4143, right? This one. So you just have to take the bra of this and take the inner product with 4121. So 4121 is here. So that means the inner product will be minus of root over of 7 by 20. So the answer you will get is root over of 7 by 20. This is the answer you will get. So I think this problem is also clear to you. Okay, let us move to the next problem. Seventh one. So please go through the question once. So let me read out the question for you. So the question is, a system of two angular momenta of respective magnitude J1 equal to 1 and J2 equal to 2. So you have given J1 is equal to 1 and J2 equal to 2. This is described by this uncoupled eigengate, which is J1 equal to 1 M1 cross J2 equal to half M2. Okay, so this system is in a state. Now they are telling the system is in a state Jm. So Jm is the coupled basis gate, right? Where J is the total angular momentum and M is the Z component of Z. Okay. Now it is telling consider in particular the states, which is in A part it is the state is so the state Jm is in the A part is J equal to 3 by 2 and M equal to 3 by 2. But in the second part B, J equal to half and M equal to half. Okay. So for each state, now you have two different values of different coupled state. The first one in A part is J equal to 3 by 2, M equal to 3 by 2. And in the second part, the J value is half and M value is half. Now they are telling for each state, calculate the probability of measuring each pair of possible values of M1 and M2 and find the expectation value of J1Z, J2Z. Okay, so they are asking about, so there will be a possible, there will be a combination of M1, M2 value. So they are asking about what is their probability and what is the expectation value of J1 and J1Z and J2Z. And in the C part is asking about calculate the expectation value of Jy in the state J equal to half and M equal to half. So this is the problem. So let us see how you can approach this type of problem. So let us see the first part. Okay. So it is given J1 equal to 1. So that means for J1 equal to 1, what will be the possible values of M1? M1 will be 1, 0, minus 1. And for J2 equal to half, what is the possible values of M2? It will be half and minus half, right? So, and so when J1 equal to 1 and J2 equal to half, so what will be the possible values of J? J will be J1 plus J2 mod of J1 minus J2, right? So J1 plus J2 will be 1 plus half, will be 1 plus half, which is 3 by 2. And mod of J1 minus J2 will be minus 1 minus half, which is half. So you will have two possible values of J, which is 3 by 2 and half. Now for each J, so like J1, J2, for each J, we will have different values of M here. So when J equal to 3 by 2, we will have M value from 3 by 2 to minus 3 by 2, right? So 3 by 2, half, half, minus 3 by 2. This will be the possible values of J. Now for J equal to half, what will be the possible values of J? It will be half and minus half, right? We will get half and minus half. Now let us see what is the initial gate, which is J equal to 3 by 2 and M equal to 3 by 2. So initial gate is J equal to 3 by 2 and M equal to 3 by 2. So M equal to 3 by 2 is the, if you see, it is a stretched gate, right? Because the maximum value of M is 3 by 2 and you will only get this value whenever M1 is 1 and M2 equal to half. In other combination, you won't get the value M equal to capital M equal to 3 by 2. So that means this gate is a stretched gate. Okay, the first gate is a stretch gate. So that means this stretch gate, you can write it as a in terms of a uncoupled eigengate. Okay, uncoupled basis state, which is when M1 equal to 1 and when M2 equal to half. So this is the coupled state which have J equal to 3 by 2 and M equal to 3 by 2. So you can write it as a, in terms of uncoupled state, as J1 M1 cross J2 M2. Okay. So that means here the value of M1 is 1 and M2 is half. It is already fixed. So that means if you want to find out what is the probability of getting M1 equal to 1 and M2 is half, this will be 1 because they are directly related, right? This, if you take the inner product of this equation 1 with M1 equal to 1 and M2 equal to half, you will get 1. This one you will get 1, and for other combination of M1 and M2 you will get probability 0. So now let us see, the next part is about, it was asking about the expectation value of J1Z and J2Z. So when J1Z acts on Jm, you already know that Jm is a stretched gate. So you can write it there. Let me erase out this one. So Jm is a stretch gate. So you can write it as a in terms of a uncoupled state with no linear combination. So that means if you act J1Z in equation 1. So if here, if in equation 1, if you act J1Z. So here you have, if you act J1Z, so what will happen is J1Z, it will act on this one, right? M1. It will act on M1 and it will act as an identity operator for this one, for this state. So that means it will give M1 H got J. Now if you take the inner the bra of this J1Z with JM, you will get M1 H got, right? Now instead of acting J1Z, if you act J2Z here. So instead of J1Z, you will act, instead of J1Z, you will act J2Z. So if you act J2Z, what will it will do? It will act on this second kid and it acts in, as an identity here. It will act as an identity here and it will directly act on the second kid. So that means you will get M2H got. Okay, if you take the bra of this J with J2Z, you will get M2H got. So that means the expectation value of J1Z is M1H got and M1 is already given, which is 1. So you will get H cut for expectation value of J1Z. For M2 equal to half, the expectation value for J2Z will be H cut by 2. So this will be the answer you will get for the expectation value of J1Z and J2Z. Now for the second part, B part. So for B part, J is different. J is half and M is half. Right? So we have different kit which is not a stretched kit. So for the second B, it is J equal to half and M equal to half. So for J equal to half and M equal to half, the value of capital M is half. So how can you get capital M equal to half? So for this, the combination of M1 M2 is like this. Either M1 is 1 or M2 is minus half or M1 is 0 and M2 is half. So that means this J equal to half and M equal to half, you can write it as a linear combination of these two uncoupled state, right? You can write it as a linear combination of these two uncoupled state. Now, what you have to do? Stretch gate expression you already know. So to find out what will be the value of J equal to half and M equal to half, what you can do, you just have to act the lowering operator. Okay, so act the lowering operator on the state gate, you will get the expression of J half and M half. So this is J equal to, so for this for fifth question, what I've done is J equal to 3 by, I have act this lowering operator on the stretched gate. So J minus is J equal to 3 by 2 and J minus acting on this stretched gate. Okay. So J minus you can easily write it as J1 minus cross 1 identity matrix plus identity plus J2 minus, right? And there is a uncoupled, these are the uncoupled state, which is J1 equal to 1, M1 equal to 1, cross J2 equal to half, M2 equal to half. So what I have done is I have just, so let me show you clearly. So this is the expression for the stretch gate, right? J equal to 3 by 2, M equal to 3 by 2. So what I have done, I have operated one J1 operator here. Okay, so I have operated this J1 operator in left hand side as well as in the right hand side of equation 1. So now if you look at the left hand side, for left hand side of this equation, fifth equation, here J equal to 3 by 2 and M equal to 3 by 2, right? So that means if you find out what is the expression for this final, uh, this state when J minus acts on it, what you have to do? You have to, you know that when J minus acts on this M equal to 3 by 2, the M will get lowered by 1. So that means you will get M equal to half here, and there is the J will remain unchanged, and there will be normalized coefficient which is h got root over of J into J plus 1 minus M into M minus 1. So J is 3 by 2, M is 3 by 2, so we will get 3 by 2 into 3 by 2 plus 1 and 3 by 2 into 3 by 2 minus 1. So that means this one you get is root 3 h got J equal to 3 by 2, M equal to half. Okay, this is the left hand side of this fifth equation. Now if you see the right hand side, we have to individually solve what will be the action of J1 and J2 on this gate. So like I said before, this J1, it will act on this operator and acts as an identity on this state. While J2, it will act as an identity on this state, but it will act on this second uncoupled state. Okay, so that means we have to find out what will be the action of J1 minus on the final, this first state. J1 equal to 1, M1 equal to 1, and we have to find out what will be the action of J2 minus on J2 equal to half and M2 equal to half. So J1, M1, it is already given. So you just have to follow the equation. So when J1 minus acts on M1 equal to 1, you will get M1 equal to 0. And there you will get a constant term here, which is root over of 2h got. And when it acts on J2 minus, when it acts on M2 equal to half, you will get M2 equal to minus half and J2 will remain unchanged and you will get a H cut here. Okay. So now you just have to put this expression 6, 7 and 8 in equation in the formula in the equation 5. So if you put it, you will get this ninth equation. Okay, just put it and you can easily get this expression, which is root over of 2 by 3, J1 equal to 1, M1 equal to 0, cross J2 equal to half, M2 equal to half, and this one is 1 by root 3, J1 equal to 1, M1 equal to 1, cross product, J2 equal to half, tensor product, J2 equal to half, M2 equal to minus half. Okay, but this is for J equal to 3 by 2 and M equal to 3 by 2. But we need to find out, we want to find out what is the expression for J equal to half and M equal to half. So for that, you use the orthogonality condition. So this state, J equal to half and M equal to half, it is orthogonal to j equal to 3 by 2 and m equal to 3 by 2. So that means you can write j equal to half, m equal to half is. So, let me explain it properly. So you just have to use the orthogonality condition, right? So this j equal to half, m equal to half, you can write it as a linear combination of this state and linear combination of this state. So for orthogonality, what you have to do? You have to change the coefficient. You have to put the coefficient of 1 by root 3 here and put the coefficient of root over of 2 by 3 here and take a minus sign. So that when you take the inner product, it's 0. Take the inner product of j1 equal to half, m equal to half with j equal to 3 by 2, m equal to 3 by 2. When you take the inner product, it will comes around 0. Not around, it will come 0. Okay, so this is what I've written in equation 10. So I have exchanged the coefficient 1 by root 3 here and minus of root over 2 by 3 here, so that this inner product of the equation 10 with equation 9, it will be 0. So this is how you can find out a state. Now to find out the probability. So probability of getting, here you can see this state have m1 equal to, if you see the first one, for m1 equal to 0, m2 equal to half. In the second case, m1 equal to 1 and m2 equal to minus half, right? So that means you will get two combination. One is m1 equal to 0, m2 equal to half. One is m1 equal to 1, m2 equal to minus half. So find out the probability, you have to take the inner product. So if you take the inner product will be nothing but the square of the coefficient, right? So for m1 equal to 0, m2 equal to half, it will be square of 1 by root 3. And for m1 equal to 1, m2 equal to minus half, it will be square of minus of root over of 2 by 3. So you will get 2 by 3 here, 2 by 3 and 1 by 3. So this is the probability of getting the combination of M1 and M2. Now to find out the expectation, so like I've solved in the first question, what you have to do, you have to act this for J1Z. So J1Z will act on the first gate, first uncoupled state, which is J1M1, and J2Z will act on J2M2. So when J1Z will act on, you take this equation 10. So 1 minute, let me erase this one first, then you can see it clearly. So when J1Z, so when J1Z acts on this, J equal to half and M equal to half. So we are acting J1Z here on this gate. Okay, so we are acting J1Z here. So for the first one, it will act on this one, right? So it will give 0 H cut because M1 is 0 here. And for the second one, it will act on this state, which is M1 equal to 1. So we will get H cut here. So that's why I've written 0 H cut and 1 H cut with the square of the coefficient, which is 1 by 3 and 2 by 3. So that means the expectation value of J1Z is 2 by 3 H cut. Similarly, for J2Z, we have to keep in mind the action of this J2Z on the uncoupled state. So when instead of J1, if we have J2Z, let's say we have J2Z, okay? We have J2Z, so what will do? It will act on this one, the first, and for this one, it will act as a identity. for the first one, and for the second gate it will act on the second, m2 equal to half. So for the first gate you will get half h cut here, and for the second you will get minus half h cut, and the expectation will be square of the coefficient with the eigenvalue half h cut, square of the coefficient which is 2 by 3 with the eigenvalue minus half. So that means the expectation of J to Z you will get is minus 1 by 6 h cut. So this will be the answer you will get. Now let us move to the next part of this question, which is the last part. So let us see what was the last part. So last part is calculate the, which is the C part, calculate the expectation value of Jy in the state J equal to half and M equal to half. So for J equal to half and M equal to half, what you can do? So we have to express Jy in terms of the raising and lowering operator. Okay. So Jy you already know it is 1 by 2y, J plus and J minus. So and when Jy acts on Jm, so you will get root over of J into J plus 1 minus M into M plus 1. For J plus it is the M will raises to M plus 1, and for J minus it will get lower to M minus 1. These are the coefficient we will get, which is for J minus it is root over of J into J plus 1 minus M into M plus 1. And for J plus you will get root over of J into J plus 1 minus M into M plus 1. So these are the coefficient we will get. Now if you see, now if you take the inner product expectation value means you have to take the bra, you have to take a bra here, right? Bra J, you have to take a bra J here with JY, right? So if you take the bra of J, so here we'll get inner product of J with Jm plus 1, which is 0 because M values are different. And here you will get a inner product of Jm with Jm minus 1. So that means you will get a 0 value here also. So that means the expectation value of Jy will be 0. So this is one of the shortest way you can solve the problem. Now let us move to the next problem. So please go through the question once. Question 8. So let me read out the question for you. So this question seems tricky, but it's easy. If you know the basic definition, then you can easily solve this problem. Okay. So let me read out. The product of position vector component x shade. So this is the product of position vector component in the Cartesian coordinate, right? So it is asking about the product of position vector component x shade in terms of the spherical rank tensor, spherical rank 2 tensor component Tm2 will be. And there are 4 options that is given to you. So now if you recall, then you can write, you have this kind of relation, right? The tensor component, the spherical rank 2 tensor component, you can write it as this expression. So for plus, for so T, so for T plus 1, okay, for T plus 1, 2, so you will get minus x z. So for plus 1, you will get minus x z. So let me write. You will get minus x z here, minus xz, and minus y, minus I times yz. And for t minus 1, 2, you will get plus xz minus y, I yz. So now you already know the expression. So you can easily calculate what is the value of xz by taking this t plus 2 and t minus 2. Okay, so if you solve it, then you will get a algebraic equation, and from that you can easily get this expression, which is xz equal to minus half t plus 1 2 and t minus 1 2. Okay, so this is based on the definition. If you know the expression, then you can within 1 minute you can know what will be the answer to this question. So the answer will be B, which is minus half t plus 2 and t minus 2. Now let us move to our last problem of this section. So let me read out the question for you. The question is, consider two angular momenta, both of magnitude j. So we have two angular momenta which are magnitude j, and let j equal to j1 plus j2 be the total angular momenta, and p is the interchange operator. And the way the p acts is given by this expression, which is p equal to p. When p acts on m1 m2, then the the m1 m2 get changed. So m1 get changed to m2 place, and m2 get changed to m1 place. Okay, so it acts as an interchange operator. Now it is asking about find the eigenvalues of p. So if you have this kind of condition, then what is the eigenvalues for the interchange operator? Okay, so how you can solve this problem? So for this, you can start from taking a eigenvector of this interchange operator. So we take, let psi be a eigenvector of p with eigenvalue lambda. So that means when p acts on psi, you will get lambda psi. Now in the second step, what I have done, this step, I have act one another operator p. So I act p again. So if you act p, then you will get lambda p times psi, right? So when p acts on psi, we will get lambda psi. So from this, we will get lambda squared psi. So that means the final expression is p. When p square acts on psi, we'll get lambda square psi, where lambda is the eigenvalue. So we need to find out what is the value of lambda here. Now let us see how we can express this eigenvector psi in terms of this uncoupled eigenbasis. Eigenbasis m1 and m2. So psi, you can write it as identity times psi, right? And this identity, you can write it as a summation over m1 and m2, outer product of m1 and m2. This one you already know, it is identity. So I have added one identity here, and I have expressed the identity in terms of m1 and m2. Now if you rearrange this, so let me clear this one. So now in this step, I have just, this one is a coefficient, right? So I have kept this coefficient here and take out this eigenvalues here. Okay. So this is the expression for psi in terms of this uncoupled eigenbasis, and these are nothing but the CG coefficient. Now let us see, when we have psi like this, then how this psi will change when p square acts on it. Okay, so when p square acts on it, this constant will remain unchanged because it's a constant only. Then only p square will act on m1 and m2. So when p square acts on m1 and m2, what will happen? So first 1p will act on m1 and m2. So 1p when acts on m1 and m2, it will give m2 m1. So this is what I was telling. So when 1p acts on m1 and m2, we will get m2 m1. Now another p will act, so you will get m1 m2 back again. So that means when p square acts on m1 and m2, the state will remain unchanged. So you can write this expression p square m1 m2 as m1 and m2. Okay. Now if you compare, so let me take a different color. Now if you compare this expression with this expression, you see that this 2 and 3 equations are same. 2 and 3. The right hand side is same. So that means this p square is equal to psi. Okay. And p square psi you already know, it will give lambda square psi, right? According to equation 1, it will give lambda square psi. So that means the value of lambda you will get is plus or minus 1. So lambda square psi is psi. So for this, from this you will get the value of lambda is plus or minus 1. So that means the eigenvalues of P is nothing but plus or minus. Okay, so you just have to uh, use the logics as well as the concept of this CG coefficient as well as the information given to you, and from that you can find out what is the answer to this problem. Now let's see the next part, which will be the last part of this section. Now in the last part, so 9b is, so that this P interchange operator, it commutes with J. So that means the commutation relation of P with J will be 0. So you need to show this, that the commutation of P with J is 0. 1 minute. So how can you start this problem? So the way to show this is like, if Pj acting on a state is equal to Jp acting on a state, then in that case the commutation of Pj will be 0. So that means let's start solving this. Let us start with Jp. So when this is already given to you, when P acts on M1 M2, you will get M2 M1, right? And M1 M2, you can write it as this J1 M1 tensor product J2 M2, right? And for M2 M1, you can write it as J2 M2 product with tensor product with J1 M1. So that means if you put this expression here, then you will get this equation 3. So that means when P acts on this uncoupled state, it interchanges the state. Like it takes J1 M1. So let me show. So it will take. So it interchanges, it takes J1 here, J1M1 here, and it takes J2M2 to here. Okay. So now, if we act J here, in the fourth equation, I have acted J here. So if J acts on it, you will get J2M2 in a tensor product J1. And J you already know. J is given by this expression, which is J1 identity plus identity J2. So that means when you act J here, then the J1 of this J1 operator will act on J2M2, and this J2 operator will act on J1M. So this is what I have written here. J1 acting on J2M2 with J2M2 and J2 acting on J1M. So this is for JP when acts on M1, M2. We will get a expression like this. So now let us check what is the expression for PJ. So J is for PJ, first J will act. So when J will be J1 identity, identity plus identity into J1, and this J1 will act on this, and J2 will act on J2. So you will get this expression when J acts on it. Now when P acts on it, P what will do? It will interchange this J1M1 and J2M2, right? So it will take J2M2 to here and take J1M1 to here. Similarly, for second one, it will take J2M2 here and J1M1 here. Okay, me, let me show you properly. So J already acts on this state. Now we are acting P. So P what will do? It will act. It will change the state to here, and it will change the state to here, to here. So now you know that J1 only acts on the first gate, right? So that means you will get J1M1, J2M2, tensor product J1M1, and the second one you will get is J2M2, cross product J2, J1M1. So this is the expression for PJ acting on M1 M2. So now if you check 6 or 7, they are equal. So that means this when JP acts on M1 M2, it is same as when PJ acts on M1 M2. So that means the commutation relation will be 0. So the P interchange operator, it commutes with the J operator. Okay. So this was the last problem to our section. So I hope all these problems I have explained it properly, and all these problems are clear to you. Let us stop for today. We'll meet on the next Saturday, same from 6 to 8. I hope all these problems are clear to you, and let us meet on next Saturday. So bye all.